Okay, yeah, so today we're going to take a look at standard form of a quadratic equation, or a quadratic function if you want to think of it that way. Either way, we looked at vertex form first. Vertex form, remember, it's a really useful form for us when we are wanting to graph a parabola, because it tells us the vertex, and by knowing the vertical dilation factor, we're really quickly and easily able to get a couple of points to the left and the right of the vertex that we can use to sketch the shape of the parabola, right? And when I see you guys in a couple years in calculus, this will be more obvious to you, but a lot of times on functions, we're not really concerned about the entire function. We're mostly concerned about what's going on in the interesting parts of the function. And turning points, where a function turns from increasing to decreasing or decreasing to increasing, are typically points that are particularly interesting to us, and for reasons that we'll talk about in calculus. And so once again, that vertex form is really useful then, because it tells us the coordinates of the vertex, and the vertex is the turning point for a parabola, right? If the parabola opens up, it's a minimum. If the parabola opens down, it's a maximum, right? Okay, so here's another way to write a quadratic function. We can write it in standard form. Now recall, with vertex form, the parameters were a, h, and k, which are very useful parameters. Here are the parameters that are going to change are a, b, and c. Not as useful to us in terms of trying to link this to a graph. Now, a means the same thing. A is a in either of those two forms. And next unit, we'll review factoring quadratics. And we'll have a third form of quadratics, which we call factored form, which also ends up using that same vertical dilation factor a. So a is going to show up in all three of the different ways that we write quadratic functions. All three forms will have the same a, but the other two parameters are going to change. In this case, the b and the c, really, it's a little more awkward to connect those to the graph, but there are some other advantages to writing it this way in standard form, okay? And we'll get to that later on. So quick review of some stuff we've already talked about. Remember, a quadratic equation, as you well know, creates a U-shaped curve called a parabola. As we've talked about already a bunch, if a is positive, it opens up. If a is negative, it opens down. As I just mentioned, the turning point of a parabola is called the vertex. When it's the lowest point, it's called a minimum. When it's the highest point, it's called a maximum. And remember that parabolas have this folding symmetry about the axis of symmetry, right, that we've talked about, that vertical line, okay? All right, so moving on then. Let's make a quick comparison. Vertex form, we're real familiar with this, right? A times the quantity x minus h squared plus k. The vertex is at hk. We know that the a is the vertical dilation factor, and the axis of symmetry is so easy to find. It's just x equals h. Now, if we want to do the same stuff with standard form, it's a little bit harder to do, right? We can't directly see the coordinates of the vertex. We have to calculate those, okay? And here's the way we can do that. The h always stands for, h and k always stand for the coordinates of the vertex when we're dealing with a function that has a vertex. Like, for example, we've looked at two functions so far that have vertices, right? That's the plural of vertexes, would be vertices. The absolute value function has a vertex, and parabolas also have a vertex, right? And in both cases, h and k are the coordinates of the vertex. So when we say h, we are referring to the x coordinate of the vertex. Well, for our standard form, we've got these three parameters, a, b, and c. Now h is calculated by the ratio of the opposite of b divided by 2 times a, so negative b over 2a. If we plug in those values of a, b, and c into this little formula, that's always going to calculate h for us, which is the x coordinate of the vertex. And for any function, how do we always find a y value if we know an x value? How do we find a y value if we know an x value? Carrie, what do you always do? If you have a certain x value and you have a function, how could you calculate the y value that goes with that x value? That's it. Plug it in, right? Exactly. We're just going to evaluate the function at that x value, right? So when we want to calculate k, which is the y coordinate of the vertex, we'll just evaluate the function at h, whatever the value of h is that we calculated, right? Okay, so when I talk about, before I go any further with this, when we talk about parameters, remember, those are like the little numbers that we're dialing in to specify a parabola. You're going to see a trend here with linear equations. Those are equations where the biggest power of x is 1. With linear equations, we required 2 parameters, right? M and B. By specifying the slope and the y-intercept, we can specify any of the infinite number of possible lines in a plane, right? When we jump the power up to an x squared, and pretty soon we're going to talk about all of these examples as being specific polynomials, but we're not quite there yet. We'll get to that word later. But when we jump the power up from x to the 1 to x to the 2, well, then what happens? We have to add another parameter. So we need an extra dial to dial in these functions. The dials could be dials that control A, H, and K in vertex form, or they could be a separate set of dials that control A, B, and C. Either way, by dialing in those values of those 3 parameters, we can create any of the infinite possible parabolas in a plane, okay? So then if we want to come up with the coordinates of the vertex of a parabola that's in standard form, this is how we do it. The x-coordinate, once again, is negative b over 2a, and the y-coordinate is whatever we get when we plug that value into the function. So what about the axis of symmetry? Well, it's really simple for vertex form. It's just x equals the h, which is the x-coordinate of the vertex. Makes sense, right? Because the axis of symmetry is the vertical line through the vertex. Well, then the axis of symmetry in standard form would just be x equals negative b over 2a, whatever that number is. Okay? So let's just get a little practice with this. How about? This is, I mean, that's really, in a nutshell, that's what we're doing, right, for today, is we're just practicing. It's just kind of a review in a way, but some of this is probably new also. I'm guessing a fair amount of this might be new. We're just going to practice doing the stuff that we did for vertex form. We're just going to practice doing that now for standard form, okay? So here's what the problems are going to look like on the assignment. Here's an example. So this is literally just a problem that I've taken a screenshot from Math Excel. Graph the equation f of x equals x squared minus 18x plus 80. Okay, and then we want to do a bunch of stuff. We want to give the coordinates of the vertex. We're going to graph the function. We want the axis of symmetry, the equation of the axis of symmetry. And just like we did in the last section, I'm going to ask you for the domain of the function, the range of the function, where is it increasing and where is it decreasing, okay? All right, so first things first, though, let's focus on the vertex. Okay, so let's see here. Liliana, how am I going to calculate the x-coordinate of the vertex? Do you remember that formula? Yes, we want to calculate h, which is the x-coordinate of the vertex. That's it, negative b over 2a. Okay, so let's do that calculation then. So we have h equals negative b over 2a. So what am I plugging in for negative b then? Here's my function. Say it again, I'm sorry.
Negative 18.
Okay, but I'm doing negative b. I'm doing the opposite of b.
Oh, so
18, good. Over 2a would be what?
over 1.
2 times 1 would give me 2. There we go, right? 2 times 1 gives me 2 on the bottom, so I get 9. So 9 is the x-coordinate of my vertex. So I'm just going to put that in my t-table right here. And if I want to calculate the y value, what am I going to do there, Maria? If I want to calculate the y value, I want to calculate k.
I honestly don't understand this part that much.
Okay, so so the vertex, remember the vertex, the x-coordinate, if we're starting off in standard form, is always negative b over 2a, right? So that's what Liliana just calculated for us. If I look at my quadratic equation up here, it's in standard form, so I could identify the values of a, b, and c. A is 1, b is negative 18, and c is 80, right? So when we use that formula for calculating h, negative b over 2a, that gives me positive 18 over 2 times 1, that gives me 9. So 9 is the x-coordinate of the vertex. And then for any function, regardless of the type of function, if I want to calculate a y value, an output value, I'm just going to plug in the input value, right? So what am I going to do then to find k? Here's my function up here. Here's f of x, and this is the x value for the vertex.
So you put in 9 for all the x's?
There you go. I just plug in 9, right? And remember, that's what we do. To find k, we just do f of h. Once we figure out what h is, what the numerical value of h is, we just plug it into the function to find k. So if I do that, k is going to equal f of 9. And so if we do that math, what's that going to give me? I'm going to get 9 squared, which is 81, minus 18 times 9, which is 162, plus 80. And so that's going to give us a grand total of negative 1, isn't it? So there is my vertex. Those are the coordinates of the vertex. And I'll go ahead and just put that on my graph right now. Over 9. So I'm over, oh, yikes. I don't think I even made my graph big enough, did I? I didn't. Darn it anyway. That's inconvenient, isn't it? Here, I better fix that. Oops, I got to do this. Hang on here. Got this thing all messed up. But that's all right. I can fix this pretty easily here. I want to do this so our notes are really good for you. Okay. Okay, something like, it's not going to work. 1 second, almost got it. Okay, that ought to do the trick. Okay, so our vertex was at the point over 9, down 1. So there's our vertex. And now all we've got to do, we could use A, is one way that we could do this. We could use our vertical dilation factor A to find some other points. And that's fine. That works just fine. If we use A, I'm not dilating this function at all, am I? I'm taking a normal parent function and I'm multiplying the parent heights by 1, which does not change them, right? And so, Natalie, remind me, for my parent function, y equals x squared, if I go 1 to the right, how far would I normally go up? Questions for Natalie. And this just goes back to that whole discussion we had, before break, we spent a lot of time on this, on my parent functions, right? We reviewed it a little bit here this week too. Okay, I'm not hearing from Natalie. How about Olivia? What's my parent function tell me to do? Normally I would go over 1 and up
1.
1, exactly. There you go. Normally I go over 1 and up 1. I would go over 2 and up how many?
2.
No. For y equals x squared.
Oh, so 4.
4. There you go. Good. Over 2 and up 4. Okay. And because a is equal to 1, I'm not multiplying those heights by 1, so they don't change, do they? And so this is what my parabola ends up looking like then. Right? It's just a normal parabola, and I can reflect everything over my axis of symmetry. And what is the axis of symmetry going to be? Let's go ahead and take care of this one while we're at it. Let's see, Rebecca Bertram, what's my axis of symmetry going to be? X equals what?
X equals 9.
9. Good. Right, so there's my x equals 9. Here's our vertical line for that. Oh, man. Let's see, I want that. Oops, there we go. Right, there's my vertical line for that. And so I could just reflect these points over my axis of symmetry, couldn't I? And now I've got some points on the other side to anchor my graph, and there's my parabola, right? So that's one way I could do it. I could take advantage of the fact that a equals 1, and I could use the vertical dilation factor. The other thing I could do, though, remember, and we talked about this just briefly a couple days ago, is just use a t-table if I want to, right? I've got this t-table. I could scoot over and plug in the value x equals 10, for example. And if I plug 10 into my function up here, I'm going to get 100 minus 180 plus 80 is 0, right? So I get the point 10, 0. And there it is. There's my point 10, 0, which I could reflect. And I could do the same thing. That just tells me, because of symmetry, I know I must have 8, 0 also, right? And I could plug in 11. And if I plug 11 in up here, I'm going to get 121 minus 198 plus 80. That's guaranteed. That's going to give me a value of 3. And there's that point, right? And I reflect that over the axis and get this point. Right? So we could do that also. To me, I think it's preferable to use the vertical dilation factor. I think it's a lot quicker and easier once there's a little more thinking initially, but once you get used to that idea, I think it's quicker and better. Okay? Give me a 1 to 5 on that so far. Are we doing okay? Okay. All right. So next one, the domain. Rebecca Edmonds. What's my domain for this parabola? And I've got the graph to look at now. As terrible a graph as that is, we can stare at that graph to get the domain in the range.
All real numbers. Negative and positive.
There you go. It's all real. It's always for a quadratic, isn't it? The domain's always going to be the same. It's like a broken record. Negative infinity to infinity. It just repeats itself over and over. What about the range? Rebecca?
It would be bracket -1 and then positive 30.
There you go. Right. So we want all values of y that are greater than or equal to -1. So we can see that on the graph. Rebecca, how could you have done that without the benefit of the graph? What would your thinking have been on that one?
The vertex, the y value is -1, and since you know that the parabola is facing up, you know that -1 is going to be the smallest y value.
Very good. Good. We know this is a minimum because A is positive and it opens up. Excellent thinking. I like it. So let's make a little, right? Whoops. Okay. Very good. So what about the largest open interval of the domain over which the function is increasing, Sarah?
Well, that would be parenthesis -1 and then comma.
Oh, whoops.
9. Yeah.
9, right? Yeah. Does that make sense?
Yeah.
Okay,
And
good.
then
Infinity, good. And how come it's 9? Because we're looking at the x values, aren't we? Right. Okay, so Sarah, while you're at it, what's the interval on which it's decreasing going to be then?
it would be parenthesis -infinity, comma 9.
Okay, good. And how could you have gotten those without the benefit of the graph?
You would just take like the x value of the vertex.
Okay, good. And remember, the vertex is a point of transition. So that's a point where the function is neither increasing nor decreasing, right? But you would know if it opens up, if A is positive and it's opening up, then everything to the left of the vertex would have to be the interval where it's decreasing, right? Correct, I should say, not right. Everything to the left is where it's decreasing, correct. And everything to the right of the vertex, and therefore the axis of symmetry, would be the interval where the function is increasing. And that would be flipped if it were opening down. Everybody see that? Okay, so you can kind of reason through this even if you don't have a graph. All right, let's try another one real quick. Why don't you just crank out parts A through F on your notes real quick, and then we'll just go through this one quickly. So take a second. Okay, what did we get? The vertex. So we need the x coordinate of the vertex, which is h. So Abby, how'd you calculate h? What you divided what by what?
I divided 12 over -4.
There you go. So negative b, that's going to be the opposite of negative 12. So 12 over 2 times negative 2 is -4. And I bet you got -3 for that. So there's my x coordinate of the vertex. Okay, which tells me, by the way, that kind of already takes care of that, doesn't it? Right now we know the axis of symmetry is at -3. Let's go ahead and add that to our chart here. So -3, that's right there. Okay. Okay. And how'd you find the y coordinate?
I plugged in -3 and I got 8.
Okay, good. So k is f of -3, and you got 8 for that. Everybody, I'm not going to, you guys all, do you get the same thing? Give me thumbs up if that's what you got. Okay, it looks like that's what everybody else got. That must be right. So -3, +8, there's our vertex. Okay, how could we, let's use our vertical dilation factor to calculate another convenient point here. So Adelaide, how would you do that? What is the vertical dilation factor in this case? Questions for Adelaide? Okay. Okay. Well, maybe you can just think through this for us now. What is the vertical dilation factor? Which is just A, right? So here's our function up here. Here's f of x. What's A? You want to try that? You want to pass? Or you want to try that, Adelaide? Okay, pass. No mic for Alan. Andrew, what's A? -2. Okay. So help me out then. How does that help us get another point? Talk me through this, please.
So basically, then you take the parent function, and then you'll leave the x value or whatever, or the x movement.
Mm-hmm.
So if you were to go over 1, you'd go down 2.
Okay, good. Normally I'd go over 1 and up 1, but we're going to multiply that normal height, which is 1, times -2, which tells us that we're going to go over 1 and down 2. Good job. Okay. Okay, keep going. I cut you off. Keep going.
Oh, and then I think you would go over 2 and down 8.
Okay, good, because we could go over, if we went over 2, we normally would go up 4. But we multiply that by -2, which means that we're going down 8. Good, so there's 3, there's 5 more. So that puts us right there. Good job. And then how could I get some freebies?
You can reflect those points over the axis of symmetry.
There we go. There we go. And so now we've got our points. All we've got to do is just sketch the parabola through those points. And there it is. Okay, everybody give me 1 to 5 on that. Good job, Andrew. Okay. All right, so that's something for this group. I really want you guys to be familiar with that. So if you're not, and it would be normal not to be in complete command of that concept yet, but that's a goal you need to set for yourself. So if that means going back and looking at a video again, or coming in to see me during office hours, or asking a question now is a great time. But we want to make sure you get to the point where you can do this stuff by using that vertical dilation factor. Okay. Now, plan B would be we could just use a t-table, and that it's going to give us the right answer, but it's going to be a little more time consuming a lot of times to do that. So if we took a point 1 away from -3, well, a convenient one would be something like maybe -2. If I plug -2 into my function up here, I could get an answer pretty easily, right? And I could even use, if I've got access to some technology here, like let's say I've got access to Desmos Scientific, for example. Let's remind ourselves real quickly how we could leverage the Desmos Scientific to make our lives a little bit easier here. Right, I could just do something like this, couldn't I? I could just say, I guess I don't even need that whole thing, do I? I could just do something like, I could say, let me roll up a little bit. Oh, there's our function, right? I guess we need that for a second. So we could introduce our function, f of x equals -2x squared minus 12x minus 10. And then we're just plugging in values, right? We could do f of -2. Oops. And it tells us 6. Okay. If I do f of -1, telling us 0, right? So that's really all. If I get those 3 out of it, that's helping us quite a bit, isn't it? Come on. There we go. Here, I'll put that on there for our notes. How about? Okay, so that's giving us those other values. F of -2 is 6. F of -1 is 0. And I can do those manually too. And there we go. It gives me those points, doesn't it? And then I could just reflect those over the axis to get the reflected points. Okay, but I really do want you to know how to use the vertical dilation factor. Okay, what's the domain for this one, Andrew Saxton?
It is -infinity, +infinity.
Good, and we can just say that as all reals. And then what's the range?
It was.
Oops, I think I went to the, that's what I meant to do. There we go.
It is 8, or -infinity and 8, right?
Okay, and I need to know brackets, parentheses.
Oh, parentheses, -infinity, 8, bracket.
There you go. Which is the same thing, remember, as saying y is less than or equal to 8. Okay, while you're at it, where's this increasing?
From -infinity till -3. So it'd be -infinity, -3, bracket.
Okay, bracket?
Yeah, bracket.
How come
Parentheses.
how come bracket?
Because that's like the peak, kind of.
Right, but remember, that's the vertex, and at the vertex, that's a transition point. So it's not actually increasing or decreasing there. So we need parentheses. Okay,
Right.
does that make sense? And then
Yeah.
obviously that's gonna be negative and -3, infinity, right? In parentheses, we're not including the -3. Okay. Okay, good stuff. Let's try one more of these here. So this time we could calculate. We got a little tougher coefficients this time, don't we? A is -1/2, B is -7, C is -41/2. So if I want to calculate the vertex here, H is equal to negative B. Everybody agree that's positive 7 divided by 2 times negative 1/2 is just negative 1, right? So I end up with negative 7. Okay, and that's telling us, oh my goodness, why do I keep doing this? That's telling us the axis of symmetry, isn't it? So the axis of symmetry is x equals negative 7. So let's plug that one in. Negative 7. Yikes, that's clear over here, isn't it? So I didn't pick a very good graph for this one, did I? There's my axis of symmetry. If I want to calculate k, which is the y coordinate, I got to plug that back into my function. And let's see, what's that going to give me? Yikes, if I plug negative 7 in, I'm going to get negative 1/2 times 49. So I'm going to get negative 49 halves plus 49, which is positive 49 halves, minus 41 halves. So that's 8 halves, which is 4. If I plug that stuff into my function. So negative 7 comma 4, there's my vertex. Okay, now I want to use that vertical dilation factor to calculate my other points. Chloe, what's the vertical dilation factor?
Negative 1/2.
Okay, good. So we know A equals negative 1/2. So help me use that to generate another convenient point here. Here's my vertex.
So would one not be a convenient one then?
You're right. Good thinking. One wouldn't be convenient because I'm going to end up getting a fraction, right?
Yeah.
Okay.
So go over 2.
Okay. Normally I would go up how much?
2 or 4.
4. Okay, good. So normally I would go up 4 to there, but I'm going to multiply 4 times my vertical dilation factor of negative 1/2, and what do I get?
Negative 2.
Negative 2. Okay, good. So we're actually going to go down 2, and there's going to be a convenient point. And really all it takes is 1, right? If I had gone over 1, normally I'd go up 1, so I would have been going down 1/2. So there's another point if I want to add another one. But that gives us our shape, doesn't it? We're just going to get something like that. And I could have used the t-table if I wanted to. But do you see that this is quicker, everybody? I mean, once you get the hang of it, this is definitely quicker, okay? Let's see, what's the domain going to be, Dawson?
Would it be negative infinity?
Yep, exactly. All reals. What's the range?
4 negative.
Okay, how am I going to write that?
Negative infinity.
Yeah, right. I have to move in the positive x direction, right? So the left end point has to go on the left, which is a negative infinity, is my left end point, right? And then what's my right end point? 4. Brackets or parentheses? Brackets, good. And we could have done that without the graph by knowing that here's our vertex, right? The vertex has a y coordinate of 4. And because A is negative, that tells me I'm opening down, right? So I could have done that even without the graph. Would everybody agree that because this is opening down, it's going to be increasing to the left of the axis of symmetry, right? So all values of x that are less than negative 7, and it's going to be decreasing to the right, so all values greater than negative 7. Okay, give me a 1 to 5 now. But give me a 1 to 5 on that. Okay, you can type it in chat if you want to. I just really want to get an idea where everybody stands on this so I know. It just helps me proceed with the lesson if I get an idea where people are on this. Okay? Okay. Looks like we're moving closer to the target here. That's good. Okay. Next issue. Okay, this is kind of, I've been looking forward to this one. So what do you think, and this is just an honors topic, this is kind of just especially for you guys here, but I've got a table that shows the percent of workers that stayed in their chosen field from who knows what that chosen field is, okay? Starting in 1990, okay? And we want to make a prediction of the percentage of workers that are predicted to stay at their job in the year 2008. What do you think here, Dulup? How could I maybe do something like this?
I'm not entirely sure.
Okay, anybody have any ideas how we might be able to come up? And this is where math, a lot of times in the real world, is extremely useful to us. So we can generate models for making accurate predictions. Any ideas? Have we done anything like this? Andrew's got an idea. Okay, and Maria had an idea. Linear regression, is that what you're going to say, Andrew?
Yeah, no, I saw Maria's in chat and I was like, yeah, that's it.
Okay, there you go. So regression, only this time, if we look at those points, it's pretty clear that it's not linear, is it? Right? If I graph those points, let's see what happens here. I happen to have this already pre-built. What do you know? What are the odds of that? And so if we look at this data, look what it looks like. That doesn't look linear, does it? What does that kind of look like to you? Adelaide, what's that look like to you? That's not a line. What shape is that making?
A parabola?
Yeah, it looks like a parabola. Or a much friendlier way of saying that is a smile, I guess. Yeah, sure. Okay, so it looks like a parabola. So the kind of regression that we want here is probably not linear, right? We're going to want quadratic regression, aren't we? Okay. But the good news is it works exactly the same way in Desmos, right? It works exactly the same way. How did we do this in Desmos? Well, we built a table, right? And all I did there is I just transcribed the information from our table. And I said that we wouldn't have had to have done this, but just so the numbers are smaller, I let the year be the number of years since 1990 when we started the data, right? So 1990 is 0, 1992 is 2, etc., right? All the way up to 2000, which is 10. So I just transcribed all that data into our table. Remember how we do that? We just use the plus add item and we pull up a table, right? And then we can do regression and we can pick any kind of quadratic regression we want to here. We could define, for example, let's use a standard form. Well, then all I'm going to say is that for my x1s and y1s that are represented in the table, I would say y1 is approximated by, so there's my tilde, the parameters a times the input x1 squared plus b times x1 plus c. That's just standard form, right? I'm defining A, B, and C, lowercase a, B, and C as being my parameters. And look what it does for me. It tells me, if I turn this on, well, look what it did. It fit that to a parabola. It's a very good fit. It tells me that R squared in this case is 0.9986. So it's almost 99.9% fit, right? Very, very good fit. And it tells me the values of those parameters. It tells me the value of A. So my dilation factor is just a hair bigger than 1/10. Tells me the values of B and C. Okay? Everybody see that? That is so cool that Desmos does that easily. I could do the same thing for vertex form if I want to. Now, because I already used the lowercase a in this example, I used an uppercase A here. Okay, so I used y1 is approximated by uppercase A times the quantity x1 minus h squared plus k, and look what it did. it gave me those values. Now, is it an accident? Does it surprise you that the values of A it gave me were identical? How come, Andrew? Why is that not surprising to you?
Well, it's the same equation. It's like the same numbers and stuff. They're just two different equations. So.
Right. Okay, good. They're just two different forms of the same function, aren't they? And the A is consistent between those two forms. So we should get, if Desmos is smart, which it is, we should get the same A value back both times. And notice that the strength of the correlation here, the R squared, is the same also for both of them. But this time it's giving me the parameters A, H, and K. So it actually gave me the coordinates of the vertex when it's in vertex form. And once again, if I turn that form on, it's the same fit, isn't it? Right? Okay, so how could I answer this question then? We've got the question here. We want to make a prediction about the percentage of workers, right, based on this data, that would stay at their job in the year 2008. So how am I going to use my model here to answer that question, Jace? Questions for Jace? No Jace. Kendall, help me out.
What was the question again?
So how am I going to use that model that I just built? Oh, darn it anyway. This class needs to be a little longer. We just have so much cool stuff to talk about. Okay, we will wrap this up on Friday. You should be able to get a pretty good jump on this, though. Most of the assignment you'd be able to do. In fact, you probably can do the whole thing. But I'll go through a couple more examples on Friday. Okay? Sound good? All right. I'm here after school if you need me. Otherwise, I will see you Friday. Have a great day.